briefly explain my internship project report titled EV ADAS Dashboard using STM32 Bluepill, PiximLab and Python. This report describes the complete development and implementation of real-time dashboard for monitoring the electrical vehicles along with the basic ADAS features. The report begins with an introduction to electrical vehicles and ADAS. Electric vehicles are becoming increasingly popular because they are environmentally friendly and energy efficient. At the same time, the modern vehicles use ADAS technologies to improve driving safety by providing features such as collision warnings and blind spot detections. Based on this concept, the objective of my project was to develop a centralized dashboard that monitors both vehicle performance and safety information in real time. In the next part of the report, it explains the proposed system and its architecture. Um, in this project, the STM32 Bluepill microcontroller acts as the main controller. Since the product was developed in a simulation environment, PiximLab was used to simulate the accelerator, brake, motor temperature, battery state of charge, and ultrasonic sensors. The STM reads these sensor values, processes them, and sends the data to Python dashboard through UART communication for serial communication. The report also explains the hardware and software tools used, including STM32Cube for embedded programming, PiximLab for simulation, Python for dashboard development, Matplotlib for graphical visualization, and PySerial for serial communication. These are the components. Then the main section of the report describes about the implementation of project. Sensor data is first collected and converted into digital values using the ADAS of the STM32. Based on these inputs, the controller calculates the important vehicle parameters such as speed, motor torque, battery state of charge, regenerative braking, and the estimated driving range. Along with vehicle monitoring, and the project also implements ADAS features such as forward collision warning, blind spot detection, time-to-time collision estimation, parking assistance, and overspeed warning. In addition, a fault detection system continuously monitors abnormal conditions like monitor overheating, communication failure, low battery level, and generates warning alerts whenever it is required. Another important section of this report explains the Python dashboard. The dashboard receives the real-time telemetry data from the STM32 and displays it using graphical components such as speedometer, battery indicator, speed history graph, bird eye ADAS view, and a warning panels. This allows the user to monitor the complete status of the vehicle through a single interface. Finally, the report presents the testing process and the results obtained. The system was tested under different operating conditions, and the results showed that the dashboard correctly displayed all the vehicle parameters. The ADAS features responded accurately to obstacle conditions, and the fault detection system worked reliably. Overall, this project explains the complete journey of this project, from understanding the problem and designing the system to implementing, testing, and validating the EV ADAS dashboard. So now I would like to demonstrate the working of the project through the simulation and dashboard videos. Our project is implemented using the STM32 Bluepill microcontroller and a Python-based dashboard. The STM32 acts as the main controller while the dashboard displays all the vehicle information in real time. Here the potentiometer simulates the accelerator, brake, motor temperature, and battery state of charge. The STM32 reads these analog inputs through the 12-bit ADC. We also use three HCSR04 ultrasonic sensors to detect the obstacles at the front, left, and right sides of the vehicle. Based on these inputs, the STM32 performs all the vehicle calculations. It calculates the vehicle speed, motor torque, battery state of charge, driving range, and also supports eco, normal, sport driving modes. During braking, the system implements regenerative braking, which helps recover a small amount of battery energy. The controller also executes the ADAS functions using the ultrasonic data. It performs forward collision warning, blind spot detection, time to collision calculation. If an obstacle is detected within the safety limit, the system immediately generates warning alerts. At the same time, the controller continuously monitors for abnormal conditions such as high motor temperature, low battery level, and communication failure. Whenever a fault occurs, it activates the corresponding alarm and warning conditions. Finally, all the processed information is transmitted through UART communication every 100 milliseconds to Python dashboard. The dashboard displays the speed, battery level, motor temperature, driving rate, alarm status, and the bird's eye view nearby obstacles, allowing us to monitor the complete vehicle status in real time. This is all the complete working demonstration of our EV ADAS dashboard. Um, yeah, you can see here it is displaying all the values. Thank you.